Oh, that's perfectly fine. Did you turn it in by email? Okay. I was out of town over the weekend. My wife's parents are in their mid 80s and they've been stuck in their house for weeks and months on end now. And they wanted to get away. They had a place up on Smith Lake, and they wanted us to come join them because they're in the mid 80s. They can't do things. So we went up there, and I mowed and cleaned up, and my wife sprayed poison ivy and all this kind of stuff, and we had a good time with them. But the internet up there was incredibly slow and weak, and more if two people were on with their phones at one time, everything bogged down. So I could not, and I had no way to print up there anyway, so I could not check my emails up there this weekend. We came back last night and I got some caught up in Blackboard, but I didn't get anything caught up on emails. So I'll try to be catching those up, but I'm in class now until, except for a 30-minute break for lunch, I'm in class almost solidly. One 15-minute break, a 30-minute break for lunch. I'm in class until 5:45 this evening. So there's not going to be much opportunity today, but maybe this evening I'll be able to catch up a few emails. Whether I get back to Saturday, I don't know, but I'll try to. Um, Someone else had a question, I thought. Okay. Whoever asked the, yeah, okay. When we finish, let me see, we're in 4.2 right now. We're almost through with 4.2. In fact, we'll finish that very quickly today, hopefully, knock on wood. Then we'll get to 4.3, and when we finish 4.4, that's your first test. Oh, I got Sharika here. Hold on, let me get her in here. Okay. All right, we should be up to 15 students now. Well, she's still not. Okay, now she's coming in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, she made 16. All right, good. Okay, an earlier question that was asked, I wanted to repeat the answer because I didn't have the recorder on at the time. If you have not yet turned in your syllabus acknowledgement page, turn it in. Okay. If you haven't, give me a research paper topic. Give me a research paper topic. If you haven't turned in week 2 homework, turn it in. Week 3 homework, turn it in. We're now in week 4. I don't put the silly little deadlines on it that Blackboard does. So if you see something that indicates it's really in bad shape or something like that, ignore it because that's something Blackboard's doing. And I was saying before, I really hate it that they have the package running the class, and I hate that. I really want to run my own class, but they have this template in place that we can't do anything with, or I haven't figured out how to do it yet. So anyway, I will anytime you get me work, just now I say this because this happened in my first class too, almost the same question, but it hasn't happened in this class yet. Well, it has sort of, but I've caught them all. Some people will turn in something with no name attached, but if I catch it before I delete the email or the Blackboard message, if I catch it, then I write your name on there. But there was somebody in my first class, I was doing my wife's iPad and I didn't notice I printed it and the printer was in the other room. I deleted it, went in and picked it up, and then realized that well, sometime later I realized they didn't have a name on it. But I had done a whole bunch that evening and I couldn't figure out which one it was. I've got to go back through all my emails and see if I can find the email that this is the one, deleted emails. That's a pain in the neck. So 2 things I ask. I'll probably ask more than this, but right now, please put your name on everything you turn in. And if it's a past homework, put which week it's responsible for. Again, week 1 was your syllabus acknowledgement page and your research paper topic. Okay. Week 2 was week 2 homework, week 3 was week 3 homework, this week is week 4 homework. So put down which week it is so I'll know which one to mark you for. Okay? Did that answer those questions? I take silence to be assent. So, all right, good deal. Let me then go and right at the end of my last class, I just got pummeled with questions. So I only had like 8 minutes left, 6 minutes left, I think, by the time I answered all the questions. I had to go downstairs and pick up something. My dog decided she wanted to go out, so I put her out while I was getting something out of the garage, and I came back in. She was still out. I went out looking for her. I couldn't see her anywhere, but she was right behind the big old pine tree, just sitting there watching. It's a beautiful day out. She was wanting to stay out. I said, no, you got to come in. So that's why I was late getting up here. And then I didn't have everything set up. So hold on just a moment here, and I'm going to see if I can delete some files here. I thought I could from this menu, but I can't. So this is going to take just a moment. I'm going to get rid of this. Okay. Screen sharing stopped. I realize that. I'll be back with you in just a moment. This one I'm going to delete because that was my first class. Okay, let me get rid of yuck. There's just too many things open here. Okay, finally I got rid of that one. And there's one more I want to lose, I think. That's this one. But actually, I don't want to lose it. I want to change it to this class. And we're in, I don't think this last example is on the slideshow, but I'm going to check just to make sure. 4.2. It's taking a long time for PowerPoint to load. Okay. Okay, let's see if this is. Yes, it is on here. Okay. All right. Okay, so we'll be starting with this slide, and then I know you can't see it, but hang with me a moment here. Let me minimize that and also open this one. Okay, and then we'll be ready to get going as soon as I can get PowerPoint to open. There it is. Okay. Now we're ready for a new slide, and we're going to start with 4.2, which is right there. All right, and we'll start from the slideshow, from current slide. And my question to you here is, oh, here comes Damien. Let me get him in here. Okay, let me just see if I've got everybody here. It says 17 students, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yep, looks like I've got them all. Okay, now next thing I've got to do, and you can't see this, but I can, is I've got to move this taskbar out of the way because it's blocking the PowerPoint. And also, Azora, you're kind of in the way. I'm going to scoot you to the right, so now you're taken care of. So let's now go to okay. We did this pre-example here in class last time. Does anyone have any question about how we did it? Okay. If not, here's the next one. And unfortunately, they show you too much. Okay. It says, how do you use a calculator to find trig functions? Okay. Now this one we didn't need a calculator. At least I hope you don't need a calculator for this one. But I'll show you how to do it on it. Now I'll show you on mine. I'm using my iPhone. It's my wife's old iPhone. Okay. And this mode will not get it to you because we're dealing with sines, we're dealing with pi's, not on this. This is just a simple little cheapy calculator. If you turn it sideways, then you get the full scientific calculator. Okay? Now, on an iPhone, or at least on this iPhone, I have to enter the argument first. That's this right here, the 2 pi over 3. So that's what I'm going to enter first. 2 times, and then the pi key is down here near the bottom, right there. You can see the pi key. Pi divided by 3. Now, I'm going to press equal sign then, and that will give me 2 pi divided by 3. Now, here's a quick check to make sure you've done things right. Okay? Now, pi is just a little bit more than 3, so something a little bit more than 3 over 3 is something just a little bit more than 1, and 2 times something just a little bit more than 1 is just slightly more than 2, and sure enough, this is just slightly more than 2. So that makes me feel like I'm in good shape. But when you notice here, this doesn't have a degree sign by it, so that means we're in what mode? Radian mode. Now on the iPhone here, you see right up here it says RAD. That means what mode you're in. Down here it says DEG. That would be if you want to change to degree mode. We're in radian mode, that's where we want to be, so we're fine. So now I have the argument done, 2 pi over 3. Now I press the sine key. And you see the sine key is right here. See the sine key, S-I-N? So I press that key, and that, nothing happened. I have big fat fingers and a little bitty key. There's your result. 0.866, 0254, blah, 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 blah. You don't need that many digits, okay? Now, this is if you had a real scientific calculator. This is a telephone. On a real scientific calculator, most of the time, all you have to do is press the sine key first, and it opens the parentheses for you most of the time. And once that parentheses is open, you do 2 pi. You don't even need the times key. On this one, you did. Okay? So it's 2, I had to do times pi, divided by 3. Then close the parentheses. That's your argument there. That's what I had to do first. And then you press enter. I had to do the sine key. I got the same answer. You have to know your own calculator. This is probably good for a TI something another. There may be a Casio that does a little bit different syntax. Maybe your phone is a variety, whatever the other one is, not iPhone, but the other kind of phone. And so maybe you'll have a different syntax, and maybe a newer version of iPhone will have a different syntax. So you'll have to know your own phone. Now, I said, did someone got a question and someone just accidentally turned the microphone on? Okay. Now, as I said, you should have known this answer already, because this is one of our favorite angles, sine of 2 pi over 3. Now, if you can imagine here, and I'm going to go on and draw it for you because it's, well, I've got to find, oh, there it is. Find my thing. I'm going to draw you sort of a unit circle, Okay, if I can get, there it is. Okay, I don't draw circles well, so don't laugh at how terrible this is. Okay, there's a circle. I'm going to put my axes through it. That's supposed to be a vertical line, and that's supposed to be a horizontal line. Okay, now, okay, someone's got his microphone on. I don't think you realize that because I'm overhearing what sounds like a phone conversation. And Courtney, I think it may be you, okay? Because I see your lights on and your microphone's not blocked. Okay? If that's someone trying to ask me a question, please say it a little more clearly. If it's someone who just has a microphone, aha, thank you. Okay, never mind. All right, 2 pi thirds. Okay, pi thirds is just about up here somewhere. 2/3 pi would be somewhere right about over here. So this is the angle we're talking about, right there. Okay, well, if you could trust my figure, which you really can't, this looks like this would be a 1/2 here, because remember this is a unit circle 1 0 0 1 -1 0. So someone let me get by with that. That's a -1/2 here. This would be a 0 -1. Now if that's -1/2 here, this up here would be the square root of 3/2. So let's see, that's what I think the sign of that should be, because that's the opposite side, which is the y angle, the y value. That's it in the unit circle, the y is √3/2. So we got as an answer, catch this down, 0.866, well there it is on the screen. I'm now going to do square root of 3/2. So how I do that, on this calculator I have to press the 3 first and then the square root key. Square root key is right over here. The glare is bad. That's 1/x. There's the square root of x. So I've got 3 in there. Press the square root of that and then divide that by 2. Okay, divided by 2 equal, and look at that answer. 0.866, 0.254, blah, 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 blah. Okay, so if you had written down this as your answer, square root of 3/2, that would have been an exact answer. This is an approximate answer. Not only do you have all those digits coming after it, you have an infinite number of digits. They keep going forever and ever and ever without ever repeating. The square root of 3 is an irrational number. Sine of 2/3 pi is an irrational number. Okay, so any questions on how they got that? Okay, the B part here says the cotangent of 1.5. Do you see a degree symbol here? The answer is no. So you stay in radian mode. But this hasn't got a pi in it. You just enter 1.5. But that's your argument. Okay? But there is no cotangent key. Okay? If you look there, you see a sine, a cosine, and a tangent. There is no cotangent key. Okay? So what we got to do is the tangent of that. Okay? So I'm going to press the tangent key. That gives me a big old huge number, but then I'm going to take its reciprocal, which is that 1/x key we saw here right there. So I'm going to press 1/x, and that gives me 0.070914.844 blah 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 blah. That's their answer. Now, how they did it, because they have a different syntax from me, okay, they opened the parentheses here because they knew they were going to have to do the 1/x key. Now theirs was x to the -1 1, mine was 1 over x. Those two keys mean the same thing. Okay? So since they knew they were going to have to do that at the end, they opened with the parentheses, then they did the tan key, which opened its own parentheses, then they did the 1.5. They were in radian mode because there was no degree symbol there. Then after they typed in 105, they closed this parentheses for the argument. Then they closed this parentheses, which gave them the tangent. And then they pressed the 1 over x key, or x to the minus 1, which is what I did last. And I didn't have to press enter. It immediately gave me that answer. Okay. Now, we got to figure out where 1.5 radians is. Well, we know that 1 radian is here just a little bit less than pi thirds, just a little bit less. Okay, half a radian would be half a pi. Half a pi. Pi halves radians would be, pi is 3.14, so half of that would be 1.57. So this is awfully close. This would be right up here. And the tangent, as you get close to 0, is undefined. So this is going incredibly large. That's why that gave me something like 14. But then when you did the reciprocal of it, cotangent, that was something incredibly small, 0.0709. So that's a really small number. That makes sense. Okay? Once you get used to the unit circle, it can be your friend because it sort of tells you, hey, you couldn't possibly have that answer. Oh, or that looks pretty close. It won't tell you exactly, but it will tell you pretty close. All right, here's somebody else trying to come in the classroom, I think. Kelly, oh, she was here. She must have had to come back again. Now that gets us up to 17. For a moment it said 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, we got everybody accounted for, I think. Okay. Now, any questions on example 3? And by the way, if I didn't say all this at the beginning, we're in chapter 4, trigonometry, 4.2, trigonometric functions, the unit circle. And we were just finished page 274, which was the last example in this section. Now, I'm turning off my calculator to save a little bit on my charge. Didn't use much, but I'm going to plug it back in just to build it up. Let me get a drink of water too. I didn't even have a chance to get a drink of water between classes. It was that rushed. All right. After every example in the text, of course, there is a checkpoint. Okay, there was example 3. There's a checkpoint. Please try to do these checkpoints as soon as you can after class. They're very similar to the example just done, and the audio-video solutions for these are found at larsonprecalculus.com. An absolutely free website we talked about before. Now, before you go there, the answers are in the back of the book anyway. So go to the back of the book. If you got it right, move on. You don't need to go to Larson. Whoa, here comes Courtney back again. Evidently he got booted out and he's back. I'm pretty sure I had him here. Yes, I did. Okay, so we should still be at 17 students. I hope that's right. All right. So let me minimize this. Any questions on section 4.2? All right, this won't advance without my clicking on it. That is the last slide in the section. Let's do the vocabulary, the top of page 275. Now, if you don't have a book, here's what the vocabulary is. Under the exercises, and the vocabulary are those in this section 4 first problems. So let's do those as a group. So that means you answer, okay? That's what that means. All right, number 1. Each real number t corresponds to a point xy on the blank blank. Any ideas? What's the name of this section? Trigonometric functions, colon, the blank blank. Can you read that? Unit circle. Whoa! Okay. My book must have hit something. And it's trying to end PowerPoint. Okay. I'm going to discard that anyway. So we're through with it. So sorry about that. Number 2. A function f is blank when there exists a positive real number c such that f of t plus c is always equal to f of t for all t's in the domain of f. Okay? Now this is back very beginning of this section. Page 2. I thought for sure it was right there on the very beginning. Ah, here we go. Not exactly the beginning. It's on page 273. Okay. Oh, wait. Here comes Morgan. Now, was she already here or not? Yes, she was already here, so she must have had to come back. So we should still be at 17, yeah. Okay. Now, on page 273, remember the question was, a function f is blank when there exists a positive real number c such that f of t plus c is always equal to f of t for all f's in that domain. Okay? Periodic. Excellent. Okay? Number 3. The smallest number c for which a function f is periodic, your answer to the last one, is the blank of f. And the word you're looking for here was inside that word you just said. Period. The period of f. Excellent. Number 4. A function f is blank when f of minus t is equal to minus f of t. And blank when f of minus t is equal to f of t. What is it when, if you go this way a certain amount and that way the same amount, but you go out, say again? Which one? The first or second? No, the first one's odd, the second one's even. Even if they're the same on either side, that means f of t is equal to f of minus t. They're odd if they're opposite signs on either side. F of minus t is equal to minus f of t. Very good there. Y'all are catching on to the vocabulary. Homework exercises here then would be either 5 or 7, both at Calc Chat. Number 9 or 11, they're both at Calc Chat. Any of the odds 13 to 21, they're all at Calc Chat. Any of the odds 23 to 29, they're all at Calc Chat. 23's at Calc View. 31 through 35, they're all at Calc Chat. 31's at Calc View. 37 to 41, they're all at Calc Chat. 37's at Calc View. 43 through 47, they're all at Calc Chat. 49 is at Calc Chat. 51 and 53 are true false. There should be both at Calc Chat. 55's of conjecture, so any of the odds 55 through 61, they should all be at Calc Chat. 55's a conjecture, 57's the error analysis, 59 is using technology, and 61 is one you can think about doing if you'd like. So any questions on 4.2? Okay, we're halfway through the first test. For whoever was asking earlier, we're halfway there. So let's get out of this one. If there are no questions, I'm going to get out of. It's on pages 275 and 276. All right, good deal. And yeah, you've had most of that assigned before. Only those last few problems probably I didn't assign last time. Okay, so some of that is repeated. Okay, let's see. Courtney is back in. Evidently, he's getting kicked out and back in a lot. Here he's back. Now we're up to 18 students. Oh, Courtney's in twice. No wonder. Courtney, you can't vote but once. Okay, no matter who says it. Okay, never mind. I didn't say that out loud, did I? Okay. All right, there we're back down to 17. All right. Now we're ready to go to a new sharing, and this will be 4.3. Still in chapter 4. Still 17 students here. Trigonometry, and we're now going to, let's go from current slide if I can get that to show up here. There we go. All right. Chapter 4 is still trigonometry. We're now doing right triangle trigonometry, which I like. That's what I grew up on. Later we did unit circle, but boy, this is what I remember trig as. Now I've got to move this toolbar, taskbar, whatever you call it, out of my way again. It keeps getting in my way. So now it's as far out as I can push it. Let's see, Matthew, you're kind of in the way too. No, you're not. You're fine. Well, I can't get it. No, you were fine. Okay. So, 4.3, right triangle trigonometry. Okay. Our objectives here are to evaluate trigonometric functions of acute angles. Anyone remember what an acute angle is? Not a cute little angle, an acute angle. Less than 90 degrees, perfect, or less than pi halves if you're thinking in radians. And we'll use a calculator to evaluate some trigonometric functions. We've already done that. Okay, we'll use fundamental trigonometric identities, yes, and get used to those. We're going to be using those now. We're going to be using those in every section after this. We'll be using those big time in the next chapter. We're going to get to know and love our fundamental trigonometric identities. Get to know them. And finally, we'll use trigonometric functions to model and solve some real-life type problems. All right, so let's go again. These must be important. They get repeated over and over again, the 6 trigonometric functions. But this time we're going to refer to them not in terms of the unit circle, but in terms of a triangle. Okay? Not just any old triangle. This section introduces trig functions from a right triangle perspective. Now, what do we mean by right triangle? Anybody? One of the angles in that triangle has to be 90 degrees or pi halves. Okay? Now, it's represented by the little square in that corner. That makes a very special triangle. It's called a right triangle because this is called a right angle. The Greeks called it that because they considered the right angle, the 90-degree angle. For some reason, this is so aggravating. My chair has rolled over my yuck. I'm about to yank everything down here because my chair rolled over my microphone and headset line, and it was yanking it all over the place. So let's see if I can get it back again in safety. Okay, that's better. Okay, sorry about that. The Greeks considered a right angle a perfect angle, and that's why they called it right. Because guess what? In your houses, do you want your walls slanted? No, they tend to fall down that way. A right angle, perpendicular to the floor, is going to stand. Okay? Everything that way. That's where your greatest strength is. That's why doors have right angles in them. Greatest strength there, okay? Now, if you have a good arch, that's pretty good too. But if you're going to do it, you don't want an angle, because then the weight is unevenly done. So right angles, perfect angles, the Greek call it. That's why they called them right. Consider a right triangle with one acute angle labeled theta. Well, guess what? Both of these angles, if that's a right angle here, these two have to be acute angles. Why? Anyone know? These two angles have to be right, acute angles if that's a right angle. What's the sum of the three angles of any triangle in the world? 180, or pi, okay? Now, if the total is 180 and this one down here is 90, that means these two added together must be if the sum is 180, this one's 90 degrees. And what are two angles called whose sum is 90 degrees, as long as they're positive? They are acute. If two acute angles added together, they are complementary angles. Not with an I, but with an E. They complete a right angle. Okay, so these two angles must both be acute angles, and they're complementary to each other, complementary angles. Okay, that's not said here, but it is true. So let's label one of them theta. So that's the angle we're interested in, not the one up here, but this one theta. Now let's look at that right triangle. This side here is adjacent to theta, okay, because one of its theta's sides is that side right there. The other one is opposite that theta, okay, and of course the one opposite the right angle is called the hypotenuse. And guess what? This is true of any triangle. The side opposite the biggest angle is the longest side. The angle opposite the smallest angle is the shortest side, and the side opposite the medium angle is the medium side. It almost sounds like the Three Bears stories, doesn't it? Okay, never mind. Okay, so relative to that angle theta, this angle right here, the three sides are the hypotenuse, the opposite side, and the adjacent side. Hypotenuse is always adjacent to either of these two angles because it's opposite the right angle, okay? But the other side, the shorter side adjacent to that angle theta, is called the adjacent side, and the third side over here is the opposite side, okay? Now, using those three sides, remember what it is. Here's the angle theta, opposite, adjacent, and hypotenuse. Here are how, using those lengths of those sides, notice nothing has to be unit 1. Nothing. The hypotenuse doesn't need to be 1. This side doesn't need to be 1. That side doesn't need to be 1. We're away from your unit triangle now, unit circle now. These can be any size angle. This could be a tiny little right angle, a great big right angle. It doesn't matter. These relationships are going to hold as long as it's a right angle here, and this angle is the same angle on all those different size triangles. The same ratio works. Using the lengths of those three sides, you can form the 6 ratios that I just said that define the 6 trigonometric functions of the acute angle theta. And they list them again: sine, I don't like this order, sine, cosine, tangent, cotangent, secant, and cosecant. That's the order I like them. You can put them in any order you want to. I know why they do them this way, but it just seems a little awkward to me. Okay? Here are those definitions. The following definitions is important to see that the angle theta has to be acute, has to be between 0 and 90. It's in the first quadrant, and that for such angles, the value of each trigonometric function is positive. Okay, so for all acute angles, all 6 trig functions are positive. We'll go and get to them later that they're not, but for these 6, these in the first quadrant, these acute angles, 6 trigonometric functions are defined as follows. Excuse me. I've got to get, for some reason, my head is draining on me pretty badly. I don't know if this ceiling fan is blowing too much air or what, but I'm having trouble breathing. Sorry. Yuck. Okay. Now, if theta is that acute angle of a right triangle, and there's 2 of them, but pick one of them, these are defined. Notice that the functions in the second row are reciprocals of those in the first. So that's why I like to do them this way. The sine of any angle theta that's in a right triangle, remember it's got to be a right triangle, is the ratio of the opposite side over the hypotenuse. Cosine is the adjacent side over the hypotenuse. The tangent is the opposite over adjacent. Cotangent is adjacent over opposite, exactly the reciprocal of that one. Secant is hypotenuse over adjacent, exactly the reciprocal of that one. And the cosecant is the hypotenuse over the opposite, exactly the reciprocal of sine. Now, the OPP stands for opposite, adjacent, and hypotenuse. Okay? And the opposite is the side opposite that angle theta. Adjacent is the length of the short side adjacent to theta, and the hypotenuse is the length of the hypotenuse, which is always opposite the right angle. Now, the very first term, I think, it's been a long time, but I think it was the very first term that I taught trig. Back then, the campus in Bessemer was the Bessemer State Technical College. I introduced this, and this is how I learned it. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, and then the others are reciprocals. Now, let me back off before I started teaching. When I was in grad school in Nebraska, I had an undergraduate as a roommate one time. We shared an apartment, and when he was doing his trig, he used this one. I didn't really like it too much, but I'll show you what it is, and then I'll tell you why I didn't like it. He used this acrostic or acronym. He called it SA, Ka, Toa. Well, to me, Sa and Ka, it sounds so similar to each other that what good is that? I mean, I have to know which one is which. I've heard some students later say they learned it as SOHCAHTOA. And if you say SOHCAHTOA, then that makes more sense. That has to be the O, that has to be the A. Now, to me, I just assume remember it, sine is opposite over hypotenuse, cosine, because that's how I had to do it. But then the first term that I taught at trig at Bessemer State Technical College, a student in the class said she learned it this way. Some old hag caught another hag taking oats away. Same here. Some old hag caught another hag taking oats away. Well, that was fine, and that was a little catchier. It was better than SOHCAHTOA or SOHCAHTOA in my mind. I hadn't heard anyone pronounce it SOHCAHTOA yet. But it was pretty catchy. But then later, a few years later, I had another student say, well, she learned it, and I like this one much better. Some old hen caught another hen taking oats away. Still oats, but now it's hens rather than hags. And I like hens better than hags anyway, so I like that one. So if you don't remember any other way, some old hen caught another hen taking oats away. And then remember that cotangent is reciprocal of tangent, secant is reciprocal of cosine, and cosecant is reciprocal of sine. Okay. Everybody got it? Get to know them. These are very, very important. Now, time out a moment here. Here's what I wanted to say about the unit circle. On the unit circle, let's go back to this picture. The unit circle, the hypotenuse is always 1. The opposite side, the vertical side, is always y. And the adjacent side is horizontal, so that makes x. So just remember, hypotenuse is 1, opposite is y, adjacent x. Look at what happens here then. The opposite side, y, hypotenuse 1. Sine was y. Cosine was x over 1. Cosine was x. Tangent was y over x. And cotangent was reciprocal x over y. And secant was 1 over y. And I'm sorry, 1 over x. And the hypotenuse and the cosecant was 1 over y. Okay? So, there is your unit circle. And to me, it would have made more sense to introduce this first and then say, and with a unit circle, the hypotenuse is always 1, everything works. Okay? Otherwise, and I've seen students do it so many times, on a test, you'll have something where the hypotenuse is not 1, and they'll give me the cosine as being x. No, it's the x over 1. Okay. So, no, I'm sorry. It's the x adjacent side over the hypotenuse. Sorry, that's what I meant to say. All right, so here's example 1. Use this triangle here, right here, to find the values of all 6 trigonometric functions. So let's start with sine of theta, cosine of theta, and tangent of theta. Cotangent of theta, secant of theta, and cosecant. I like to write them this way. If you like them vertically or horizontally or something else, that's fine. Okay. Now, where do you want to start? Sine, cosine, tangent, cotangent, secant, or cosecant, or does it matter to you? Name it and claim it. Anybody? Sine. Okay. So you remind me what the sine of any old angle theta is going to be. Okay. I don't put the 3 letters. I just put the first letter. Okay. Now, do you see in this drawing over here which would be the opposite side for theta? 4. You're absolutely right. This is the opposite here. How about the hypotenuse? Oh, look at that. He knew it was 5. How did you know it was a 5? Absolutely. Now, for those who aren't familiar with a 3, 4, 5 triangle, here's how he got it, whether he realized it or not. Remember that x squared plus y squared is equal to r squared. On a unit circle, r is 1. Here it's 5. Well, here we don't know. So we have that 3 squared plus 4 squared, this is Pythagorean theorem, is equal to h squared. Agreed? Please say yes. All right, good. So this would be 9 plus 16 is equal to h squared. Okay? And 9 plus 16 is 25 is equal to h squared. Take a square root of both sides and you get h is equal to technically plus or minus 25, plus or minus 5, but in reality 5. Here's something to remember, and we're right now in the first quadrant where everything's positive. But remember this, your hypotenuse is always positive. Always, always, always. If your angle had been over here, I'm sorry, that's the same one we just did. Over here, I just did it again. over here. Okay, so your x would be negative here, your y positive here. The hypotenuse is always positive. The hypotenuse is always positive. Okay, I shouldn't have drawn the on this. So this is your 5. So once you know that hypotenuse, can you write down what the sine is? Anybody? What? It's pretty easy. What's your opposite? Where did my pen? 4/5. I just can't get my pen to show up. Come on, oh, there it is. 4/5. How about the cosine? What is cosine? Caught another hen. What would that be? 3/5. Taking oats away, that would be 4/3. Cotangent would then be 3/4, the reciprocal of tangent. And secant would be 5/3. Perfect. Okay. And cotangent would be 5/4. You see how easy that was? My goodness. Whereas before, on the unit circle, you've got to find out your x's and the y's. You got to find out where you are, Waldo, and find out what the x and y are. With your right triangle trig, if you know 2 of the 3 sides, you know all 3 because of Pythagorean theorem. Okay? So identify your 3 sides, your adjacent side, your opposite side, and your hypotenuse. If you know 2 out of 3, you know them all. And once you got those down, fill them in. Sine is always opposite over hypotenuse. Cosine is always adjacent over hypotenuse. Tangent is always opposite over adjacent. The other way I'll look at it is to sine over cosine. If you did this right here and do 4/5 divided by 3/5, the 5's cancel out and you get 4/3. So that's basically how I do it. I don't worry with that anymore, but it all works. It all works. Okay, so that's how we did it. Let's see how they did it. Any questions before I go on to them? Okay, they say by the Pythagorean theorem, the hypotenuse squared is the opposite squared plus the adjacent squared. It follows that hypotenuse is the square root of 4 squared plus 3 squared, opposite squared over plus adjacent squared, and that would be the square root of 25, which is 5. Remember this, hypotenuse is always positive. Adjacent and opposite can be positive or negative. Hypotenuse is always positive. Okay. Now, once you got that, then it's just fill in the blanks. So the 6 trigonometric functions are sine is opposite over hypotenuse, which is 4/5. Cosine is adjacent over hypotenuse, which is 3/5. Tangent, they do it right. Tangent is opposite over adjacent, which is 4/3. And then they go up and do cosecant from here. That would be hypotenuse over opposite, which is 5/4. Secant is hypotenuse over adjacent, which is, I like to do it right next to what its reciprocal is. Reciprocal of cosine, which is hypotenuse over, the cosine is caught another hen, adjacent over hypotenuse. So this is hypotenuse over adjacent. I can't talk. 5/3. And then the cotangent is adjacent over hypotenuse, which is 3/4. Okay. Once you have the 3 sides, if you have any 2 of the sides, you can get the 3rd side. Once you have them, fill them in. It's that easy. Okay. So in example 1, you are given the lengths of 2 sides of a right triangle, but not the angle theta. Often, you'll be asked to find the trigonometric functions for a given acute angle theta. To do this, construct the right triangle having theta as one of its angles. Now here are our favorite angles of all time. Goodness, my whole head is clogging up. 30 degrees, 45 degrees, 60 degrees. Now they left off 90 and 0, but you know those. That's pi 6, pi 4, and pi 3 in your radians. The sine of these we already knew was 1 over 2. Sine of 30 or sine of pi 6, 1 over 2. The sine of 45 is root 2 over 2. Sine of 60 is root 3 over 2. You can think of this as root 1 over 2, root 2 over 2, and root 3 over 2. Root 1 is 1. Okay? The cosines of those go in the opposite directions. Root 3 over 2, root 2 over 2, and root 1 over 2, or 1/2. That's for cosine of 30, 45, and 60, or pi 6, pi thirds, fourths, and pi thirds. And then the tangent is the sine of a cosine, okay, which would be, the 2's will go out. It would be 1 over root 3, which is the same as root 3 over 3. This will be root 2 over 2 over root 2 over 2. That's just 1, okay? And this will be root 3 over 2 over 1 over 2. The 2's go out, and you're just left with a root 3, which is the reciprocal of, well, wait, we'll come back to that later. Okay. So, any questions on these special angles? Okay? Get to know them. They're your friends. They'll get you out of all kinds of trouble. Okay. In the box, if you notice this, that the sine of 30 is the same as the cosine of 60. Okay? Which is the same as sine of pi 6 is the same as cosine of pi thirds. Okay? Now, one thing to note, 30 and 60 are what kind of angles? They're both acute. You're absolutely right. What special kind of acute angles are they? Complete a right triangle. They're complementary angles. They add to 90 degrees. 30 plus 60 is 90. Pi 6 plus 2 pi 6 is 3 pi 6, which is pi halves. They add to pi halves. They are the same. So if you ever wonder where the co came from, this was sine and this was cosine. If the sine of 30 is 1/2, then the complementary sine of the complement of that angle, cosine of 60, is also 1/2. So that's what we mean by that. That's where the co comes from. The sine of the complementary angle of this is that. Okay. Same is true here. The sine of the complement of 45 is 45, so the cosine of 45 is same as sine. That makes tangent 1. Okay. Or pi fourths, pi fourths, pi halves. And then these do the same thing. The sine of 60 is the same as the cosine of 30. Both of them root 3 over 2. That's what they're saying here. In the box, note that sine of 30 degrees is 1/2, which is the cosine of 60 degrees. That occurs because 30 and 60 are complementary angles, and these are the complementary functions, cofunctions. In general, it can be shown from the right triangle definitions that the cofunctions of complementary angles are equal. The cofunctions of complementary angles are equal. That is, if theta is an acute angle, then the following relationships are true. The sine of the complement of theta is the cosine of theta. The cosine of the complement of theta is the sine of theta. The tangent of the complement of theta is the cotangent of theta. The cotangent of the complement of theta is tangent theta, and the secant of the complement of theta is the cosecant of theta, and cosecant of the complement of theta is secant theta. That's what the co means, the C in front of the name. Meant complementary. Losing the voice again, sorry. Man. Any questions? All right. By the way, we went through page 277 and 278. Okay. We skipped example 2. Sorry about that. And by the way, there is a little blurb, and I think I'll show it to you. Here is a little blurb on the side of the page. Historical note: Georg, I can't read it backward, Joachim Rheticus, I think is how you pronounce that, lived way back. That's 1500s, isn't it? Or is that 1200? I'm reading it backward. Oh, 1514 to 1576. Not an extremely long lifetime, but 62 years was probably a good lifetime back then. Was the leading Teutonic mathematical astronomer, that means of Germanic type origin, of the 16th century. He was the first to define the trig functions as ratios of the sides of a right triangle. Okay. So there's a potential paper topic. Of course, this can't be your source. This can be your source of the idea. You need to find a source outside the book. This wouldn't be enough to do a paper on, but you can find a source. And as I said before, I hope I've said it before, after every example, there was example 1, there is a checkpoint. And the checkpoint's found audio, video. Yeah, I think I went over that before. Okay, so let's do example 2. We did example 1, but not example 2. There, we've gone on and done the block. We got to do 2 and 3. So let's go back. I think I'll go to the whiteboard. That one I can't erase. Okay, now that I've gone to whiteboard, I also have to move some things around because Bennett, you're in the way again. No, you're not. You're okay. Oops. There you are. Okay. Got to move my whiteboard. It all looks white to you, I think. That's what I've been told anyway. But I've got a smaller whiteboard than I have screen, so I have to move the whiteboard to fill up as much screen as I can without blockage. Can't get it all, but got most of it. So here's example 2. Find the values of the sine, and we've actually already done this, of 45 degrees, the cosine of 45 degrees, and the tangent of 45 degrees. And while we're at it, let's go on and do the cotangent of 45 degrees, the secant of 45 degrees, and the cosecant of 45 degrees. Now, yuck, this thing is so aggravating. Okay, now there's a couple of ways you could do this. You could go back to your good old unit circle if you wanted to. Actually, a little bit easier way to do this. We need to draw a right triangle. Ooh, that's awful. Let me see if I can do better than that. Okay. I think this time I'll try to draw with straight lines. I tried before. Okay. Now, this is so aggravating. Okay, here we go. Let's just say those are 2 straight lines, and let's just pretend they're the same length. I think I've got this one a little too long. Okay, but let's pretend, and then we'll pretend this is our hypotenuse. Okay, now if I've drawn those correctly, if this is indeed, let me go back to my draw mode here, if this is indeed 45 degrees here, that's our angle theta, 45 degrees here, what would this angle up here have to be? Anybody? 45 degrees. You're absolutely right, because these are complementary angles to each other if indeed I drew this properly and this was a right angle here. This is so aggravating. Okay, if that's a right angle, then those have to be. Obviously mine's not exact. Okay, but here's the thing. If these two angles, remember I said the side opposite, the shortest side has to be the smallest side, and the side opposite the smallest angle has to be the shortest side, and the side over the median. Well, these two angles are the same. So that means these two sides, this side and this side, have to be the same. Now, if you had to pick a number, a pretty simple number for to be the length of that side, what would be the easiest one? Easiest would be 0, but that wouldn't have any length at all. So let's not use 0. After that would be 1 and 1. Now, if those two sides are 1 each, what does that make the hypotenuse? One squared plus 1 squared would be 1 plus 1 is 2, root 2. Hey, didn't know you'd be doing such high-level math today, did you? 1 plus 1 is 2. All right. Now, there you have a representative triangle. It's not a unit circle one. We did use ones here, but they weren't ones for your hypotenuse. These are ones for your sides, and this would have to be root 2. So here we can write down our answer, can't we? Sine of an angle is some old hen. What would that be here? Anybody? Opposite side is 1, hypotenuse is root 2. But if you don't like having that radical in the denominator, that can be written as the square root of 2 over 2. This is not writing 2's well at all. It's just awful. Okay, square root of 2 over 2. How about cosine? What would that be? Caught another hen. The adjacent side is also 1 over root 2, which is exactly the same. That is the square root of 2 over 2. And what would the tangent be? Taking oats away. Opposite side is 1, the adjacent side is 1. That's equal to 1. Okay? Cotangent is exactly the reciprocal of that, and that would be 1. Secant is exactly the reciprocal of cosine. Now I want to use this form for secant, because if you reciprocate that, you just get root 2. And if you reciprocate this, you also get root 2. There you have the 6 trigonometric functions. They only ask you for 3, but we did all 6 of a 45-degree angle. Okay? Do you see why that's true? The other way to look at this is this line here. If you, well, where is it? The hypotenuse here. Where in the world is my cursor? I can't get it. Come on. Oh, there it is. Okay. There it is. If you put your origin here, then this is the 45-degree angle. That's the identity function, the one-to-one function. So whatever your x value is, your y value is the same. Okay? all the way up until you get 1 over 1. But 0.3 over 0.3, 7/10 over 7/10, 45 over 45, 83 over 83. It's going to be the same. That ratio is going to be, of those two, is going to be 1. That's why tangent and cotangent is equal to 1. There we go. Goodness gracious. There it is. Those are both 1s. And these would be 1 over root 2 here, root 2 there. Now, I think I've mentioned this to you before, but let me say it again. Sine and cosine are always going to be numbers between -1 and 1. Always. A root 2 over 2 is going to be about 0.707. That's in between -1 and 1. In fact, it's in between 0 and 1. Sine and cosine have to be between -1 and 1. Tangent and cotangent can be anywhere in the world. They can be tiny little angles or numbers or great big numbers. Any number in the world. All real numbers. However, the secant and the cosecant, because they're reciprocals of sine and cosine, they've got to be outside of -1 to 1. So they could be less than -1 or greater than +1. And by the way, square root of 2 is greater than 1. That's about 1.414. Greater than 1, perfectly fine. Now they can also be equal to 1, just like sine and cosine can be equal to 1, but sine and cosine can never be greater than 1 or less than -1, and cosecant and secant can never be between -1 and 1. They've got to be outside, less than -1 or greater than +1. So there we've done example 2. Now let's do any questions on 2 before we move to 3. All right, let's clear the drawings here. Yes. Oh my goodness, we're supposed to stop at 11:15, weren't we? Why did you let me go so long? Okay. We will begin next time with example 3. I've got to get my eraser here and wipe that out. Thanks for telling me. I just looked at the clock and I mistakenly was thinking we went to 11:45. That's the next class. Thank you so much. Let me give you homework exercise. That's what you're supposed to be reminding me. Don't forget to give us homework assignment. Why didn't I hear someone say that? Okay, homework assignments will be, whoa, this is a long section. Starting on page 284, any of the odds 5 through 9. They're all at Calc Chat, 5's at Calc View. I think you can also do any of the either 11 or 13. They're both at Calc Chat. And then we'll turn around and do the rest of those later. So not too many new ones this time, but we had plenty from 4.2. All right. Thank you much. Any last thoughts, parting shots, last questions, anything? I'm going to stop the recording as